Sorry, I'm just admitting people now that just. Sorry, we're going to wait another minute, but it's okay that you're recording. It's just now everybody's showing up. Uh-huh. Who is Christopher Lee Newman?
That's Courtney Fix Newman. I don't know how to change his name on this.
It's fine. Okay, guys, I'm going to go ahead and start. I sent this morning, I had not planned on typing out what I was going to cover, but I went ahead and did that. I spent last night looking at exams and picking out similar concepts that both 1110 and 1120 students would need. I'm going to tell you right now, I'm not covering everything that's on your final exam. I am covering similar concepts from 1110 and 1120. I did that on paper, and then I thought, well, you know, I'll go ahead and type it out. So Felicia has agreed to record this, and when I send the recording to everybody, I will also send what I sent y'all earlier, like this is what I plan to cover. And I put a little bit of gaps in it so that if you wanted to rework it, you could. Are there any questions with that before I start? Okay. One of the first questions I asked was to determine the volume for a specific mass sample, but I gave a specific gravity. You guys need to recall that specific gravity is basically the density without the unit. So if I give you a specific gravity number on a problem, simply cross through specific gravity and write D and then put the unit grams per milliliter. Are you following what I'm saying?
Yes, ma'am.
Okay. So back to this problem. If I then change the specific gravity to density, you know, I put the unit on it. And I know density is mass over volume. I can solve for volume is mass over density. I can get the answer. Again, everybody, I have chosen problems that are common in concept to both 1110 and 1120 finals. This is about
Ma'am, can you put the paper up again and like back it up a little bit so I can take a picture? Thank you.
if I don't, I have to get through so much, guys. If you don't get a picture or screenshot of every problem, get at least the answer and then work it out yourself. Okay, sorry. The next problem on the packet that I emailed you says, or ask, determine the specific heat for a certain mass of an unknown liquid. I'm giving you, it's at a hot, hot, hot temperature. I'll hold this up in a minute. It's placed in 400 milliliters of water at a cooler temperature. Let's see, whose mic needs to be muted? Is it Malaz?
I'm sorry, I didn't notice.
Okay. Sorry. Again, the problem is determine the specific heat value for, I give you a mass of an unknown liquid. It's at a hot temperature, and it's placed in 400 milliliters of water. Pause. That's 400 grams of water.
You already turned on the open side, right? Okay.
400 grams of water, because the density of water is 1 gram per milliliter. I'm giving you what the final temperature ends up being when these two are mixed. I simply want you to calculate what the specific heat for this unknown substance is. Now, I don't even know that I need to show this. Francois, you do not need to take a picture of the problem. I sent it typed to you. But this is how I think you should set it up. I've tried very hard to teach, put all your hot stuff information at the top, your cool stuff information at the bottom. I'm giving you what the resulting final temperature is. So right here in this little area, I can already figure the heat involved using mass times specific heat times temperature change. Now, the next piece of paper that I'm holding up, I've plugged and chugged these numbers. Here they are. Here it is. The heat gained by the water is its mass times the specific heat times the temperature change. And we figured out that number. So if I want to equate that, heat loss equal heat gain, that's what I did here, where I'm simply solving for the missing specific heat. Do any of you have questions with this?
No, ma'am.
Okay. The next concept that I sent on the packet was nuclide notation. And just as a quick review, nuclide notation has the symbol of the element that's represented by X, the mass number, which is number of protons and neutrons, the Z number, which is number of protons. My most common example is sodium. If I look on the periodic table, it has an atomic mass of 22 point, hold on, I'll say it exactly, 22.990. Well, that rounds to 23. Its atomic number, its Z number is 11. What this symbol means is 11 protons, 11 electrons since it's neutral, and if you go 23 minus 11, that will give you your neutron count. So I have an example. What would it be for nickel 60, meaning mass number 60? The student would know 28 protons, 28 electrons. 60 minus 28 would give you 32 neutrons. Now, a student might ask, but wait, why did I put a 60 there when on the periodic table it says it's 59? Can somebody answer what I'm doing an example of? I'm waiting.
It's an isotope.
Exactly, thank you. Thank you, Julie. It's an isotope. Okay. The next problem that I had on your packet that I wanted you to review is called electron configuration. And I selected, let me put this in order. Well, nickel. Nickel. If you write out its electron configuration from the beginning, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. It has 2 valence electrons. Valence means total number of electrons in the highest energy shell occupied. This is shell 1, guys. Shell 2, 3, 4 is the highest shell number I see, so I would say 2 valence. If I wanted to abbreviate this, I would write the previous noble gas filled, so to this 3p6 is argon, 4s2, 3d8. That's the abbreviated electron configuration. If I wanted to make the nickel +2 ion, you simply remove its valence. You always remove, for metals, their valence electrons first. So I removed the 4s2, and this is the answer for the nickel 2+ cation. Y'all will thank me after I do this review. Oh, let me let this person in. Sorry. Any questions so far? I'm sorry, guys, that I'm doing it this speed, but I really, I've got a lot of stuff I want to cover, and I have to finish this by 11:45. So here we go.
We'll have the option to rewatch this on the recording.
Yes, and we can all thank Felicia now. She's recording it. Felicia, send me the link, and I will forward it to the 5 lectures. I might also forward it to Dr. Burns and Dr. Veith and the others. So just send me the link, okay?
Yeah. Yes, ma'am.
Thank you.
Welcome.
Okay, here we go. Quantum numbers. And for those of you just entering this review, I am selecting concepts or topics that are common for the 1110 and the 1120 final, just the 1110 portion. I'm not covering everything. Note, I sent you guys an 1110 review packet. Do it. I sent my 1110 people the about 30 multiple choice questions. Do it. I sent my 1120 people 2 versions, A and B. Do it. Those will be helpful. I just spent last night doing them all again to see, like, okay, how good are they? They're good. I'm just saying. Okay, here we go. Quantum numbers. Even though it says numbers here, they are abbreviated with letters. N, L, M sub L, and sometimes M sub S. I called it an S. N stands for what energy shell are you in? L stands for which subshell are you in? S, P, D, or F. M stands for, hey, which orbital are you in? The spin tells you which electron is in that orbital. Now, they have names. I'm going to go ahead and say it, but you don't need it for your final. Principal, subsidiary, magnetic, and spin. They're not going to ask you that. Don't worry about it. But what you need to know, energy, shape, orientation, I don't know, what does that say? Sorry. Which electron it is. Now, we're going to go back to nickel. Nickel had the electron configuration. The last noble gas completed was argon, 4s2, 3d8. If I simply want to know the quantum numbers for the 3d8, N is 3. That's the shell we're in. L is 2. Here's why. S, P, D, F, 0, 1, 2, 3. If I'm in a D, it needs to be a 2. How do I figure out M? Okay, I didn't write this on my paper. There are orbitals associated with SPDF, and it's a pattern, 1, 3, 5, and 7. So for D, there's 5. You always write negative the L value through, in increments of 1 to positive the L value. And then you simply place your electrons in there one at a time. 1, 2, 3, 4, 5, and then 6, 7. I exaggerated where the 8th one landed because that tells me my M value. Spin can be plus or minus 1/2. Yes, for my students, I taught a convention. But other colleagues don't use that same convention. Don't worry about it. Just know spin is only allowed to be plus or minus 1/2. Not 3/2, not minus 10, just plus or minus 1/2. Okay, now I have 2 excellent questions illustrating what I just said. We'll do this one first. Which quantum number is correct? A, B, C, or D? And then tell me why it's correct, or you can tell me why the others are not. I don't care. Which one is correct?
It's C.
C is correct. Now, let's, for everybody else, tell me why A is not correct. What makes A wrong?
Is it the -3?
Hold on. Right. This is a 4D. D's can only go from -2 to 2. You can't have an M of -3. I don't know who said that. Thank you. Okay. Why is B not correct?
Because you cannot have a plus 3/2.
Correct. That is why. Okay. Why is D, I should say, wrong? Why is D wrong?
You can have a D in the second.
Exactly. There is no such thing as 2D. Guys, now that I went over that, is that not bad? I mean, come on. That's the kind of question you're going to be asked. Okay. Oh, wait, I have another one. Hold on. I created another one. Hold on. Okay. Which one of these cannot be possible? Meaning, I guess 3 of them are correct. Which one is not correct?
Ms. Morris, is it possible that you can hold it up a bit higher?
Like that?
Thank you. Yes.
I'm actually, what did I ask here? Which is, sorry guys. Yeah, which is not possible. There we go. Oh, okay, I can see from the back of my paper. Which one is definitely wrong?
It's B.
Yeah, because this is 3S. S's can only be 0, not a -1. Could y'all follow that? You know, y'all might thank me eventually, okay? I'm just saying. Next. Okay, whose mic is, who do we hear?
Oh, let me see.
Sorry, it's fine. Okay, here we go.
Sorry about that.
There are, I'm thinking of 4 neutral atoms: fluorine, oxygen, magnesium, and sodium. And I went ahead and wrote what's called their electron configuration. I abbreviated with the previous noble gas, and then I put, you know, their valence stuff after. Now, what I want to do is make whatever these are, their common ions. So I'm gonna do this because I don't want y'all to see what I'm saying. Oops. Okay, so I'm doing their common ions. Fluorine was 1 away, so I added an electron and made it 2p6. Oxygen was 2 away. I added 2 electrons to make it 2p6. Both of those got to be, sorry, neon. Magnesium, I removed, because these two here are metals, guys. Metals form cations. I removed 2 electrons, and this one I removed 1 electron. Do you all understand what I did there? My whole goal here was, let's get to a noble gas. What is that called? What do they have in common? What's the word? It's one word. Oh,
Isoelectronic.
say it. I'm sorry, say it again.
Isoelectronic.
Correct. So that's isoelectronic. Now, perfect. That's isoelectronic. So now here's the next question about it. Which one of those ions is the largest in size? A, B, C, or D, and why?
Oxygen, because it gained 2 electrons.
Yes. This is the biggest. Which one will be the smallest?
Magnesium, because it lost 2.
Correct. Who is answering?
Me.
Well, I'm not seeing who it is. Sorry. Is it Julie?
Yeah.
Thank you. Okay, it's fine. Now, okay, here's the concept behind that, and you all need to know this. Here it is. If I'm thinking of iron, an iron atom, and it's argon, sorry, I can't read, 4s2, 3d6, and I start taking 1 electron off at a time, what happens to the size?
It gets smaller.
Right. It's going to get smaller, smaller, smallest. That was in my lecture, guys, the kidnapper in the mall. Do y'all remember that little example? Okay, good. So we're, you know, we got 5 of these done. The next question is empirical formula. I'm going to read the problem and then I'll hold up the sheet. The problem simply states, a compound contains phosphorus and oxygen. So it's P something O something. It's determined to have 43.7% phosphorus. That's all we tell you. How in the world would you get how much oxygen it has? I'm asking before I hold up my sheet.
You would add oxygen with hydrogen, and you would subtract it from 100, I think.
Okay, let's say it again. All you have, Francois.
Subtract 100, subtract 100, 43.7 from 100, and the remaining number will be the oxygen.
Correct. Here it is.
Yeah.
Okay.
Then,
100 minus that would give you the missing percent.
then we will get the mass number, and we divide each one by mass number. The smallest number, we will divide it again by the result. And
Here it is. Abdullah is telling us how to do this problem, which is fine.
Yeah.
You base it on a 100-gram sample, divide by their molar masses,
yes, the
you
molar.
get their moles, divide each by the smaller one, you get a mole ratio,
Yes.
What do we do here? What do we do?
We multiply by, yeah, you multiply by 2 because we have 2.50.
Right, this is not close enough to 2 or 3. So you have to double that, double that. Before I put this sheet down, do you all understand the process of this?
Yes, ma'am.
Okay, well, wait. What if we tell you that the true compound, y'all just figured out it's P2O5, correct? P2O5? Well, when you get that molar mass for P2O5, you get 142 grams per mole. What if we tell you in your word problem, wait, the compound is really 284 grams per mole? What you gonna do? Anybody, before I hold it up? You just figured out, I'm sorry, I didn't mean to interrupt. Somebody's gonna answer, go ahead.
Double it?
Yeah, how did you know to double it? How did you know to double that?
Guess the molar mass you gave sounded like it was twice what we found.
Right, it's right here, guys. If I gave you 284 and you figured out P2O5 is 142, that's a factor of 2. Oh, here, you just distribute, right? P4010. Could y'all follow that?
When there's whatever it was by percent, is it always of mass?
Yes. Yeah. Matter of fact, I'm glad you asked that. Let me just say you have a sample. I'm just going to write this up. Okay, Isaac, anybody, everybody, let's say I give you, you have a mass of a sample, and we give you the percents, maybe 2 of the 3. But you guys know, you told me just a minute ago, you add these 2 up, subtract from 100, and you get the missing 1. Are y'all following what I'm trying to say here?
Yes.
Okay, once you get these percents, just change it to G, G, G. You don't even need this number up here. You base it on a 100-gram sample. Do y'all remember me teaching y'all that? It's a way to save time. Isaac, did you understand what I was just saying there?
Yeah, I remember you doing that.
It is based on mass, yes. Okay, here's the next problem, and I'm hoping I'm doing it in order of what I emailed y'all. I apologize if I'm skipping around, but I am covering everything that I emailed you. Okay, here's the problem, and I'll read it and then I'll hold it up. It says, given a 2.013 gram sample of CH3CH2OH, so I'm giving you the compound. How many carbon atoms are there? Okay, this is what you do. You take your mass, you figure out the molar mass of this, convert it to moles. You use Avogadro's number, that's how many molecules per mole. You count up how many hydrogens. Is that what I asked? Oh, I'm sorry, I asked carbon. Count up how many carbons are in the compound to finish the problem. Are you guys following that? What if it had been, instead of how many carbon atoms, it had said, okay, just what if, how many hydrogen atoms? What part of this changes?
The last part.
Exactly. What number would you put in the last part?
How many had, because I can.
The carbon, we have just 2 carbon, I think.
But what if I said how many hydrogens?
You're
We
holding it a
put
little
the
close, I can't see it.
hydrogen 6.
6. Okay, that's what I wanted. There'd be 6
Yes,
hydrogens.
yeah.
Okay, now, okay, what if I asked you to draw it? CH3, CH2, OH. I had you draw it, okay? And I want to know the bond angles around, sorry, the oxygen. What is the answer, A, B, C, or D? What are the bond angles around the oxygen?
Is is A
Is it A, like Ben?
because 180?
No.
Is it D?
Yeah, it's D. Okay, we need to review. The bond angles around this carbon, there are 4 regions. That is a pure tetrahedron. That's 109.5. The bond angles here, 4. Pure tetrahedron, 109.5. Bond angles here, they're still, guys, listen, 4 regions, but 2 of those are lone pairs. So it squishes it a little bit. It's a little less than 109. Do I need to do another example of that? Because y'all need to know that. Here, I'm going to do one. Let me just draw my molecules, and they're not really showing molecular geometry, but I know I did this in lecture. Well, but for, see, the 1120s, it's been a while. Okay. Pure tetrahedron, 109.5. Still 4 regions, lone pair. This is 4 bonding pairs. This has 3 bonding pairs and 1 lone pair. This is going to be, say this is 109.5, this might be 107. Still 4 regions, but 2 lone pairs. It's not 90. If this is 109 and this is 107, this might be 105. The lone pairs start squishing the bonds closer together. Do y'all remember me covering that in lecture? Well, if not, you know,
Yeah.
now. Okay. Okay, hold on. Next question. Okay, well, I give you a molecule. CH3CO, CH, CH, CCBr, okay? And I simply want to know how many sigmas, pi's, how many carbons are sp3, sp2, sp, the bond angles around, what is it, the third one, and the last one, okay? Now, let's figure this out. Oh, well, first of all, you're going to have to draw it. Take a minute, draw it. Here it is. CH3CO, CH, CCBr. Draw it out. I'm going to give you a couple minutes. Draw it out. And then we're going to figure out these. On my next piece of paper, I've already drawn it out. But here, I'll hold this back up. It's CH3. Well, and if I sent y'all the handout, but anyway, CH3, CO, CH, CCBr. Give you another minute or two, draw it out, and we'll figure out our blanks. By doing this problem, that's going to answer for for all of you, at least 2 questions on your final. And just FYI, we never do, say, a series of questions to one molecule. I'm just trying to do concept. I was just trying to say paper. Oh my gosh, I still have like 30 more sheets to go through. It's okay, we can do this. Would you guys like me to put up the drawing?
Yes, please.
Here we go. CH3, CO, CH, CC, Br. What I had to do to make every carbon happy with 4, nothing here. Double bond oxygen there. Double bond between the carbons there, and a triple bond here. Now, once I've drawn that, do you guys see 12 sigmas?
Yes, ma'am.
Hold on, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, okay, sorry. Okay, do you see 4 pi's?
Yes, ma'am.
Perfect. Do you see just one carbon that's sp3?
Correct.
And then there are, let's see, 1, 2, 3 carbons that are sp2. And 2 carbons that are sp. Now, I know I didn't ask the bond angle for everything, but we'll go ahead and do it. What would the bond angle for your first carbon be, somebody? What would it be here, the bond angles?
109.5 degrees.
Thank you. What would the bond angle for the second one be?
120.
Yes, and so would it be here and here? What would it be for these two?
180.
Right. Okay, guys. Anybody have a question about this before I put this paper down? Okay. Next. It's I did, let's see, 1, 2, 3 or 4 problems on naming, writing the formula, and the oxidation state. So if I give you potassium chromate, you guys need to know potassium being in group 1 called alkali metals is a +1. Chromate is one of the polyatomic ions you need to know. Oh my gosh, there's like 25 of them. It's a 2-. Because this is a +1 and this is a 2-, we write the formula this way, and it's called potassium chromate. If I needed the oxidation number of the chromium only, you can either do it here. You could say +2 -8, that's got to be a +6, or you can figure it out there. Now for my 1120 people, y'all should be pretty good with this stuff by now because of redox. But everybody, 1110 and 1120 has oxidation number questions. Okay, here's another one. Name this acid. Well, if the student learned there are 4 common halogen oxyacids, per, ic, us, hypo, us, then you can figure out which one that is. If we wanted just the bromine oxidation number, you can work from the outside in, and that's what I did on this paper. Now, let me ask this. This is something new. May I put, this is something new. I just thought of something. Hold on. Oh, here, I'm going to actually even be tricky. Okay. This is a trick question. Which one of these would be the strongest acid and why?
Is I think is the first one. No.
Okay, again, I'm being tricky. Well, I'll go ahead and tell you the answer. The first one doesn't exist.
Okay.
The first one doesn't exist. Fluorine is the most negative or electronegative element. You can't have an oxyacid with fluorine. The answer is this one. Now, how would you, the student, know that? I'm waiting. All of you should know the answer to this. How would you know that this one is stronger compared to those two? I'm waiting.
One's closer to the top of the table.
Well, the answer I wanted, this is the answer I wanted. I memorized my 7 strong acids. And my 7 strong acids are the following.
You gave us list in the class, I remember.
Yeah, I know I did. And guess what? Y'all better know them. Here they are. I memorized my 7 strong acids. These 2 are not in that group. Are y'all following what I'm saying there?
Yes, ma'am.
Okay, perfect. Okay. Oh, I'm sorry. I have 2 more naming things. 2 more naming. Could somebody tell me, I should have been holding these up without the answers, how to name that compound?
Nickel 2 phosphite.
It is nickel Roman numeral 2 phosphite. Here's why. Nickel's a +2, phosphite is a 3-. So if I wanted the oxidation state of the phosphorus in that compound, you'd pull out the ion and its charge and figure out what it is. Are there any questions with the how to do that? Okay, the last naming kind of concept that I wanted to review. There are 3 transition metals. Guys, let me hold my chart up. This is alkali metal, alkaline earth metal. These right here are called your transition metals. These down here are called your inner transition metals. Do y'all remember me telling you that? There are 3 metals in this D box that have 1 and only 1 oxidation number. They're fixed. No Roman numerals needed. Do any of you remember what they are? What are the 3? Go ahead, sorry.
Aluminum, zinc, and silver.
No, aluminum is, you're right, aluminum is not a transition metal. Aluminum, sorry, is over here. Well, where is it? Aluminum is fine. I need to know the 3 metals here.
Each gold, AG, Kaizen, and something else. It's AG, CD, and then something else. I don't remember.
Right. Well, okay, Francois, you got 2 out of the 3.
And then
So-
is there one can I see it again?
Well, here they are.
It's it. Yeah.
Okay. Silver is always a +1. Zinc is always a +2. Cadmium is always a +2. They're fixed.
Correct.
Which means when you see them in a formula, like a compound, you don't need a Roman numeral with them. So what I did is I did 3 examples: silver nitrate, zinc chloride, and cadmium, permanganate. I'm just pointing out that those are the 3 transition metals that don't need a Roman numeral. Okay, next. Are there any questions before I continue? What I have is I've got, go ahead, Francois, what?
No, can you, which of the groups do we need to know like their names of, like halogens and alkalines?
Oh, yeah. Okay. You need to know alkali metals. The group 2A is alkaline earth metals. Obviously, I think y'all know the noble gases. Halogens. The oxygen group are called chalcogens. And then just know these are transition metals and inner transition metals. Okay. Anybody else have a question before I continue? I'm going to do, I still have a lot. Okay. Reaction types. I'm not covering every single reaction type. I'm just covering common ones that my 1110 and 1120 students need to review. Common one, number 1. On your little practice that I sent you, I said, I want you to complete and balance lead 2 nitrate with lithium chloride. That's your practice, okay? Well, I've got the answer here. Lead 2 nitrate, lithium chloride. Now I'm going to stop. Soluble. Nitrates are soluble. Lithiums are soluble. Strong electrolyte. Trade spots. Lead 2 chloride, and then lithium nitrate. This is a solid. This is an exception to the solubility rule. If for my 1110 people, you need solubility rules, that will be provided. 1120 people, they had a lab on that. That's not provided. You're only allowed to split apart strong electrolytes. I can't split that one up. You are allowed to cancel what are called spectator ions. Your net ionic is this one. That's called a double replacement or precipitation reaction type. Guys, on your test, it's probably going to be something like they give you a reaction. It's completed, it's balanced, it's everything. And they just want to know, hey, what kind of reaction is it? Is it combustion? Is it acid base? Is it single replacement? Okay. Now, the next reaction type I'm going to go over in no particular order. Combustion. I have an organic-y thing here. Plus O2 will always give you CO2 and H2O. That is called combustion. Yes, you'd go back in balance. That reaction type is called combustion. Remember, 1120 people, I'm doing just the 1110 review today. Yes, you guys would know how to get the oxidation number, but I'm not doing that right now. Okay, here we go. So that's that. Next reaction type, single replacement. I have a metal and an acid called hydrochloric acid. This metal is pretty high up on the activity series. It's going to displace the hydrogen. This is called a single replacement. This one down here is yet another double replacement, specifically called acid-base neutralization. Weak acid, phosphoric, weak electrolyte, guys, it's not strong. Strong base, strong electrolyte, soluble salt, why? Sodiums. Non-electrolyte, water. If I wanted to write the net ionic to this, which everybody in here has a net ionic on your final, you cannot split this up. You are allowed to split this one up. You are allowed to split this one up. You may not split that up. Here's the answer. Actually, I've shown it here on how I did not split this up, split that up, split that up, did not split that. What can I cancel? Well, it looks like I can cancel the sodiums. If I cancel the sodiums, this is what I get. Are there any questions with that? Let me emphasize something. You're only allowed to split apart strong electrolytes. Well, what are they? Your 7 strong acids, your 8 strong bases, and any soluble salt. Those are the only things y'all can split into ions. Questions before I continue, because now I'm getting into word problems. Are we good? Okay, here we go. Okay, this is a on your practice thing that I sent you this morning. It reads, if you have 3.20 grams of CH4 reacting with 6.40 grams of oxygen, I need to know how many grams of water can you collect. That's called a limiting reactant problem. But what the student, you guys have to do, you have to write the reaction first. You have to balance next. You write your 2 givens. You convert to mole. You prove which one limits. You use your limiting amount and the mole ratio to get to water and water's molar mass. This is a typical limiting reactant problem.
Just I can see the left or the right side. Okay.
So do this or this? Which
Oh,
way?
yeah, this one. Yeah.
Can you see it now?
Yeah.
Okay.
16.0. Okay.
What I may do if I have time today, on that packet that I sent you guys, before I send the recording and the recording to everybody, I'll go back in my packet and write the numerical answers on it. Because y'all need to practice this on your own. I'm giving you the answers now. Y'all need to practice it on your own if you want to be successful on this test. Okay, here we go. This is okay, this is what it said in the packet that I sent you. Determine the volume of a gas produced from decomposing gold 3 oxide. I give you the gas temperature is 22.1 degrees Celsius. I give you the barometric pressure is 749 torr. Step 1, the student has to write the reaction. You have to write that reaction. It's a noble metal oxide decomposes to form the gold plus O2. Then you'd go back and balance. Step 2 would be I give you the mass of the oxide. You convert it to moles. That's not your gas. You have to get to the oxygen. You have to use a mole ratio. This is your gas moles. That's your N. Okay, then wait. Step 3 would be, in the word problem, we have T's. I've got to convert it to Kelvin. I give you a P. I have to convert it to ATM. Why? Because I'm using the most famous gas law. PV equals nRT. V equals nRT over P. N for oxygen moles. R is the given constant. T is in Kelvin. Pressure is in atmospheres. I multiply and divide that out and I get my volume. Questions with that? Okay, that was a PV equals nRT problem. Okay, let me put that here. Next, now we've only got maybe 4 more concepts. That's good. Okay, phase diagram. Generally, a phase diagram is pressure along the y-axis and temperature along the x-axis. And the main concept you need to know, well, there's several. Solid comes before liquid, comes before gas. The point in which all 3 solid, liquid, gas states coexist is called your triple point. This is showing solid state, A. D is showing liquid state. I think that's B and, is that an E? Yeah. B and E are showing gas state. F is showing an equilibrium point between liquid and gas, and it happens to be at 1 atmosphere. Can somebody tell me what point F would be called? I'm waiting. Point F, what would it be called? Say it, somebody said it. Normal boiling point, that is correct. Normal boiling point. Could somebody tell me what the line segment AB, A to B, would be called?
Sublimation, something like that?
Sublimation is correct. Hold on. Can somebody tell me what, let's see, which other one can I do? Oh, D to A, D to A, D to A, what that would be called, D to A.
That's a liquid.
Critical.
Freezing.
Right, it's freezing. Liquid to solid, it's freezing. There we go. Okay, let me put that down. Okay, are there any questions with the phase diagram?
No, man.
Okay, next it will be, the next series of stuff will be intermolecular forces of attraction. Okay, here we go. There are forces holding molecules together, and that's why we have solids and liquids. And these forces are called ion-ion, hydrogen bond or hydrogen bridge bond, dipole-dipole, and London dispersion forces. Now, ion to ion are found in your ionic things. hydrogen, these two here, hydrogen bond and dipole, are found in your polar things. But hydrogen bond is a very strong dipole force if the hydrogen happens to be bonded to either nitrogen or oxygen or fluorine, which is on the back of this paper. I'll flip it in a minute. London or dispersion forces are found in all substances. They are very, very weak, and they're the only force for your nonpolar substances. Now, how would you, the student, know if a molecule may hydrogen bond to its neighbor? When you draw the Lewis structure for a molecule, and I've got a couple of these drawn, if a hydrogen is bonded to either N, O, or F, then that is telling you that molecule can hydrogen bond to its neighbor. Here's example number 1. Okay, I have this molecule here. I draw it. CH3, oxygen, CH2, CH2, and a fluorine. I see a fluorine there, but it's not bonded to a hydrogen. Now, on this molecule here, I draw it. CH3, oxygen, CH2, CH2, NH2. Oh, goodness. Nitrogen, which is one of the three, nitrogen, oxygen, fluorine, is bonded to a hydrogen. So this is going to hydrogen bond to its neighbor. Well, what does that mean? It's going to have a high boiling point. We don't actually care what the molecular weight is or molar mass. It's going to have a high boiling point, because here's what we're using. We're using this trend that says intermolecular forces get stronger as their molar masses increase. This just means grams per mole. Your boiling points increase and your vapor pressures drop. The exception to this trend is if you have a molecule that may hydrogen bond, we don't care about that. It's going to have a high boiling point. Now, here's the example. Oh, let me do a different example before I hold this one up. Which one of these would have the highest boiling point?
A.
I'm sorry, say it again.
A.
A, why?
Because there's hydrogen in there,
Well, there's hydrogen in all these.
and then bond with the oxygen, which is one of the three.
Correct. So this molecule here, even though it has the lowest molar mass, because hydrogen is bonded to that oxygen, it's going to have a high boiling point. Now, guys, listen, I'm crossing that one out, taking that out of the picture. Which one of these three now would have the highest boiling point?
D.
Say it again.
D.
Exactly, because it has the greatest molar mass. Right. Okay, now here's the trick. This is a tricky question. Which one of these four would have the, lowest vapor pressure?
It's going to be A.
Why?
Because it has the highest boiling point out of the four. It has the lowest vapor pressure. It's because of the hydrogen bond.
Correct.
Morris,
Yes.
I was curious on what that was, and I checked that this was actually an exception. apparently. But I wonder if we would get exactly that question on the test. Would we just rely on the hydrogen?
You need to know hydrogen bonds involve species, Lewis dot structures that are bonded to N or O or F.
I know, no, I'm saying for the boiling point on that last one,
Oh, sorry.
actually,
Wait, maybe, okay, look, back here. Intermolecular forces increase as molar masses increase, boiling points increase, vapor pressures drop. So this is an inverse relationship no matter what.
yeah, I get that. I'm just saying in the example where you ask which one has the highest boiling point, D actually has the highest boiling point.
Okay, sorry, you mean this one?
Yeah, I checked I was just wondering what the relationship between the forces was, and that one apparently is heavy enough that it's more than.
We're going by ammonia because it can hydrogen bond. They're expecting you to know that nitrogen's going to be an exception.
I understand that, but that example right there is an exception, apparently.
Okay, well, I don't know that they're going to be that picky on your test.
So we're just referring to hydrogen is over anything
Yeah,
else?
this is more like the, here, I'll do one like y'all are going to get. Let me write it out. Okay, here we go. Which one of these would have the lowest vapor pressure?
The first one.
No.
The heaviest one?
Right. This one's going to have the highest boiling point, so it's going to have the lowest vapor pressure. They all will hydrogen bond. This one has the greatest molar mass, so it has the highest boiling point. If it has the highest boiling point, it has the lowest vapor pressure. Could y'all follow that? Do I need to explain why boiling point and vapor pressure are inversely related? Here, let me do it. I'm gonna try to do it. Imagine you have a not that you're gonna have this at your house, a hot plate. And you have a beaker of water and a beaker of fingernail polish remover, which is acetone. Now, you don't turn your hot plate on at all yet. Can you smell the acetone? Yes. Why? It has a high vapor pressure. Well, if water's vapor pressure at room temperature is 22 torr, but acetone's vapor pressure at room temperature, I'm making up a number, is 340 torr. Okay, you've got a 22 and a 340. Which one will reach atmospheric pressure first? The acetone. You only have to get to 760. If it reaches 1 atmosphere or atmospheric pressure first, it's going to boil first. It will have the lower boiling point because it has the higher vapor pressure. Are y'all following what I just said? That's why that's an inverse relationship. Okay, so back to Isaac. So you looked up between ammonia and all these hydrides of the nitro or the group 5A that the antimony one is going to have the highest boiling point?
Yeah, it was apparently because the nitrogen doesn't pull that hard, or there's some sort of exception going on.
Okay, I'll look that one up. But on your test, it's not going to be, I mean, it'll be a little bit more straightforward. So. Okay, let me put, okay, wait a minute. I haven't done phase change yet, right? Meaning with heat, have I? I haven't done the heat problem with phase change, have I?
Not yet.
Okay.
Not yet.
All right, here we go. in your packet I emailed you, it should have a problem toward the end that says how much heat is released when 20 milliliters of water at room temperature, about 22.4 degrees Celsius, is cooled to ice at -13. So you've got this problem. How much heat is released? You've got 20 milliliters of water, which by the way is 20 grams. Question to the class, why? Why is 20 milliliters of water the same as 20 grams of water?
Because the density of water is 1 gram per
It's 1
milliliter.
gram of one.
Correct. I am taking that water, maybe I have it on my kitchen table, and maybe my house is pretty cool, and I'm gonna put it in the freezer. And I want to make it go down to -13 degrees Celsius. So this is the concept. I'm taking my water at this temperature and I'm wanting to cool it to ice at -13. That's 1, 2, 3 steps. 2 of the steps involve a temperature change, step 1 and step 3. This step here where my finger is a phase change. Liquid to ice or liquid to solid. I don't use heat equal mass times specific heat times temperature change on this one, because if I did, it would be 0, because 0 minus 0 is 0. So I have to use what's called the heat of fusion. So here are my 3 steps. Step 1 is mass, specific heat of liquid water, temperature change. Step 2 is mass, heat of fusion. Step 3 is mass, specific heat of ice, temperature change. Joules, 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 I add them up. Question to the class, why is it negative? Why is the value, if you have 4 choices on your test, 2 of them are positive, 2 of them are negative, how would you know by process of elimination to look at just the 2 negative choices? Somebody, I'm asking.
Because it's freezing, it's below 0.
Endothermic?
No. Okay, let me hold it up again. Hold on. How much heat is released?
And temperature is negative.
Exothermic, negative delta H. If it said how much heat is needed, hold on. If we said how much heat is needed, we'd be going, see how my arrow is going down? If I wanted to know how much heat is needed, I'd be going up. Are y'all following what I'm saying? The difference between endo and exo? Endo is a positive delta H. Exo is a negative delta H. Okay. Two more problems. This is a Hess's law or heat of reaction kind of problem. I'm giving you a goal, and this was all typed on your practice, a goal reaction. I'm giving you 3 steps. The rules are, if you reverse or flip a reaction, you must change the sign. If you divide or multiply by the whole reaction by 2 or divide by 2, you must do the same thing to that number. Now, my goal says I need a single hydrogen on the left. I got to flip that. I'll do it in a minute. My goal reaction says I need a single bromine on the left. I need to flip that. Okay, so I did that. Watch. Flipped, change the sign, flipped, change the sign. Kept, left the sign. When you add these up, what cancels? Somebody tell me what you're going to be able to cancel when you add these three together.
We can only see two.
Did y'all not see? Let me let this person in. Did y'all not get the packet that I emailed this morning?
Yes, I got it.
Okay. Okay. Well, I'll just go ahead and answer it. I added them up and I can cancel hydrogen, the diatomic hydrogen, the diatomic bromine. I canceled it. But then I have a problem. Two.
Yeah, so you have to divide by 2.
Right. You add them up and then you have to divide by 2. Everybody's going to have one of those on your test. That's why I did it. Okay. Last problem. And I think this is the last one in the packet that I sent you. It says, given 100 milliliters of molarity of an acid, and we're reacting it with sufficient base, barium hydroxide, I want to know the mass of salt produced. This is not limiting reactant. However, it is, can the student write the reaction? It's a double replacement or acid base. You have to do that first. Can you balance it? Can you convert the volume to liters and multiply by the molarity to get moles? And then you finish the problem. So I wrote the reaction. I balanced it. I took my 100 milliliters and had it in liters times my molarity so that I could cancel the liters and get just the mole. I took my mole amount, used my mole ratio, and then this is the molar mass of the salt, and I got my answer. This would be called a stoichiometric or stoichiometry problem using molarity. Why is it not limiting reactant? I'm asking the class.
You're only given one quantity.
Exactly. And I gave you plenty of that. I think in my word, I said sufficient. You're right. I only gave you one reactant amount. Okay. We have a few more minutes. Questions. And it can come from, as long as they're 1110, it can come from the practice multiple choice, the review packet, anything. But it still needs to be, because I've got a lot of 1110 people here, 1110 question. Questions? While y'all are, oh wait, they're here. Okay, I've got my 1110 stuff here.
I don't have a question. I'm leaving. Thank you.
Okay.
In the phase diagram from D to E, is that just boiling?
Sorry, let me get it.
Yeah.
No, it's fine.
Or is there like another term for that?
Oh, this one here, sorry, this one?
Yes.
Okay, you said from D to E?
Correct.
Yeah, that would be, well, they'd really call it vaporizing.
Okay, thank you.
Yeah. Okay, another question. Anyone else have a question concerning 1110? No? Well, I hope this review helped.
Yes. Thank you,
Ma'am,
Mom.
I got a question.
Okay.
It's simple as like I don't remember how to do the first because there is a question. I think it's question 6 from the test you sent us. The old one. You said which element has the greatest first
Oh, yeah. Okay.
ionization.
Yeah. Okay. There was a trend on ionization energy. Let me just let me write it up and then I'll explain it. Okay.
Okay.
The trend was increasing ionization energy up a group and left to right. However, there were dips.
Okay.
The dips were between beryllium, oh, my pencils. Beryllium and boron group, and the nitrogen and oxygen group. And here's why. The nitrogen is a P3, happy, happy, happy. And the oxygen group is a P4. So this one, nitrogen, won't let you take an electron from it. This one will. There was a dip.
Okay.
That's why the answer is letter C, because it's a P3.
Okay.
Okay. Next question.
Is the when you add salt to water and then the boiling point changes, is that 1110 or 1120?
That's 1120, but basically,
No, I'm just asking.
well, I mean, go ahead and ask. It's okay.
I just don't remember what the formula looks like.
Oh.
So I wonder if it was.
They're going to give you the formulas for the colligative properties, but let me write it up.
Can you please go over the metric conversions briefly?
I'm sorry, what?
Can you go briefly over metric conversions?
Metric conversions? Yeah, let me just show this to Isaac real quick. The change in temperature for boiling, that's how much you elevate it, is equal to the number of ions in the salt. That constant's called the boiling mole constant, and that's the molality. So if you had, I'm just making up two, like say you had NaCl, and then you maybe had aluminum chloride, right? Say you have these two, and they're the same concentration. This is going to have the higher, because it's I of 4, the higher boiling point. Did that help, Isaac?
Yeah, thanks.
Yeah, they're on your final, when they ask you, and they will, colligative property problems, they give you the formula and the constant. Okay, back to Malaz. You said go over metric conversions.
Yes, ma'am.
Do you have a particular one?
No.
Oh, you just mean like, what does that mean?
I mean briefly, like centimeter to liter to centimeter and that stuff.
Yeah, you need to know, like if, let's say I have, okay, I did a real good one on one of these practices. Hold on, I'll find it. Here's one. Okay, I'm gonna write it up and then let me write it down, I'm sorry, and then I'll hold it up and show you what I mean. This was on one of the practices I sent you, the multiple choice, it's number 12. It asked, how many cubic centimeters in 100 meters cubed. If you have 100 meters cubed and you want centimeters cubed, you know you're going to have to cancel the meter cubed. You don't worry about these cubes right now. There are 100 centimeters to a meter. But if you cube both of those, you're canceling that unit. And you're going to get a very large number. The answer is like 1.00 times 10 to the 8th cubic centimeters. Okay, that's just one example. Let's say I give you, you've got 2.05 inches, and I want to know how many millimeters, say. So we have, I'm just setting it up and then show you what it is. So 10 meters to 1. Okay, I give you 2.05 inches, and I want to know, sorry, how many millimeters. Well, you've got to convert your inches to centimeters and then cancel your centimeters to millimeters. Now, English to metric will be like, I'll circle. This in the center would be provided. The English to metric will be provided. Did I answer your question?
Yes.
Okay.
Is Fahrenheit to Celsius provided?
No.
Is that just
it's like, is it 5/9? Is it 9/5? What is it? Do we add 32? Do we, I don't think y'all have to worry about Fahrenheit to Celsius.
So, ma'am, to be clear, all the formulas from the gas law, all the 6 one, we have to know them all, right?
Yes. For 1110 students, y'all are responsible for all formulas except calorimetry stuff, meaning heat. Well, there were 2 ways we gave it. Let me show it. One way, this pencil. Let me use my pen. Sorry. I'm going to write it both ways, and I'll be honest, I'm not sure which way we wrote it on the test. Q, heat, is mass times specific heat times temperature change. That is the only formula, that we provided on the 1110 final. We did not provide PV equals nRT or 22.4 liters per mole or Graham's law or any of them. We did not. Now, 1120 people, sometimes the formulas are in the problem. If they're not, you have, I think what Dr. Burns is going to do is put next to a periodic table a list of constants and then formulas, because that's usually provided for the 1120 final exam.
I think he already sent out, for my class at least, he already sent out the sheet.
Okay, is it on chemistry 1120 all labs?
I'm not sure. Let me check.
Yeah, if you could check, and then before we close this meeting, because some of my students might need to, you guys just check your chemistry 1120 all labs. He may have already sent, hey, these are going to be provided, or please print these out. I actually think Dr. Veith did the same thing on the chemistry 1110 all labs for the periodic table, in case you don't have a clean one. What I mean by that, when you all go to take your test, you're going to have to show a non-written on chart.
Will the activity series table and solubility rule will be provided?
It will only be provided if there's a question concerning that. So you do not have to have that memorized.
I don't think.
I'm sorry, what?
I don't think he posted it for the lab.
He didn't post it in the lab?
No, I don't think so, not yet. I don't see it in there.
Okay, Ira, could you forward the email he sent you guys, and then I'll forward it to my students?
Yeah, let me go find it.
Thank you. I mean, no rush, just sometime today so they'll have an idea of what you're talking about.
Sure.
I have a quick question about the oxidation state. Does that just mean like what's the oxidation number or?
Yes. Yes.
Okay.
Yes.
Can you explain me the 27 from the old test, from the practice one you said?
Number 27 on the multiple choice one?
Yes, ma'am.
It says assuming ideal behavior.
Yeah.
Okay. How about I just do, oh, okay. Here we go. This is the formula.
So is the molar mass of the 22.4? Okay, so my question is, do I put 32 or 16?
Yes, Francois, it's diatomic.
Okay.
If you forget your diatomics on this test, I'm just saying, and I don't mean to like be calling you out. Guys, if you forget your 7 diatomics, you're going to miss at least 4 questions.
Okay, I was just wondering.
Well, don't forget, there, have no fear of ice cold beer, or hey, this is the better way, guys.
I have no fear of
No, this is the better way. You find your 7. You find your nitrogen 7. You make a 7. And then you remember little piddly hydrogen over here. Those are your diatomics. Find your 7. Make a 7. Of course, your noble gases are not diatomic. Make a 7. Then remember hydrogen. Or the have no fear of, I don't know, in high school, did y'all learn Brinkelhoff? Never mind.
I did.
Okay.
Yeah, I used that one.
Okay, there we go. Anybody else have a question? Oh, before we leave, since I have quite a few of my 1120s here, I'm doing a review of similar to what I just did today, but only 1120 concepts, and it will be Tuesday at 6 p.m. till 7:30 or 8. I will send an email with the link.
I think I wouldn't be able to make it to that one.
You're not? Sorry.
Yeah, it's fine.
It's okay. It's fine. I'm sorry you're not going to make it, but I'm sorry.
Is there going to be somebody recording the lecture?
I don't know. I might talk with Mallory and see if she'll do it.
Okay, thank you very much, Miss Morris.
Yeah, I mean, if somebody records it, I'll definitely send it to everybody. Anybody else have a question before we close this meeting, or before I end the meeting? Guys, before we end, if you do, okay, I'm referring to the 1110 people now. If you do your concepts for review packet, and you do your multiple choice practice thing that I've already given you the answers, you guys will be A-okay. Now, 1120 people, if you do the 1110 packet, and you do at least Dr. Burns' letter A1, because I mean, I went through, see all these check marks? They're all 1110 concepts. Oh my gosh, he's got more 1110 concepts on here than he does 1120. But they're good review.
Do you have your own packet for 1120?
I haven't sent out an 1120 packet at all. I do have one, but, and I don't have it up here with me. I instead created a multiple choice sort of practice thing.
Mm-hmm.
And I can send that out. I was waiting to see, my colleagues chose a couple of my questions, and I was waiting to see which one, so I have to delete those and then maybe put a couple more in. But I was going to work on that and send that out on Monday.
Okay.
Yeah, but this is Ira talking, right?
Yes, yes.
I'll include you.
Okay, thank you.
Yeah. Did he not send y'all an 1120? He's been sending y'all a ton of stuff.
We have a lot of 1120. I was wondering if you had your own, because sometimes I do both.
Yeah. I do have an 1120 review packet that, let me ask my students that are still here. Would y'all want, you know how I sent y'all the 1110 review packet? Would you want an 1120 review packet that's similar to that?
Yes.
That would be nice.
Yes.
Okay.
Yes, please.
I can send it. Let me make my note. I'll do that like today.
Because for the midterm, I did your packet and I found it really helpful.
Yeah. Well, yeah. You're welcome. I know.
A lot of people borrowed it from me because they were like freaking out they didn't get a copy of it.
Yep, I get it. I know. Okay. As soon as this meeting is over, I will go find this review packet and send it to both of my 1120 classes, and Ira, you will be included. You can share it with whoever. I don't care.
Okay.
Yeah. Okay, guys. It's
Thank you so
Saturday.
much.
Are we good?
Yes.
Yes, ma'am. Thank you so much.
Thank you.
You're welcome. Guys, like I said before, I'm glad I'm thinking about this. I have not finished grading that 1120 test, that test 5. I definitely haven't done it for the night people because they're still taking it. But for my day people, I will say that was like very time consuming on my part to go try to look at scrap paper. So I did get 3 emails last night. Please grade mine, please grade mine, please grade mine. So I'm assuming the rest of you, that's going to be your drop grade, unless it was, okay. And I don't mean to say this, but I don't think Felicia cares. Felicia, obviously, I'm going to keep yours because you made a 40 out of 40. Okay.
Yes, ma'am.
I get it. But for most of the students, they did not do well. If you want me to regrade your test, I need the email. I've only received 3. Now that was, announced in class and all that, but because otherwise I'm not going to go back and regrade. Yes, I'll post your grade. I'll post what you've already seen, 17 out of 40 or 21 out of 40. Well, change it to the percent, but they're awful for the most part. Anyway, okay, guys, I have to go. It's been fun. Good luck on all your finals, not just chemistry, all your finals. If you have a question concerning a concept and you're just struggling with it, send me a quick email. I don't know, I guess I live by my phone. I check my emails a lot and I'll respond. Okay? Bye, guys.
Bye,
Thank
ma'am.
you, Ms.
Thank you so
Morris.
much.